We often hear about the dangers of high blood sugar, but rarely do we visualize the catastrophic mechanical and chemical erosion occurring inside our own vascular network. This is not just a metabolic inconvenience, it is a systemic assault on the 60,000 miles of blood vessels that sustain your life. Over the next 30 minutes, we will dissect, layer by layer, exactly how hyperglycemia dismantles human anatomy, from the largest arteries to the microscopic capillaries of the eye and kidney. To understand the damage, we must first understand the defense. Lining every vessel is the endothelium, coated in a delicate, hair-like mesh called the glycocalyx. This slippery, negatively charged layer repels blood cells and regulates permeability. It is the gatekeeper of vascular health. In a healthy state, it prevents adhesion and produces nitric oxide, the gas responsible for vasodilation. But high blood sugar attacks the structure first, shaving off this protective coating before a single symptom is felt. When glucose levels remain chronically elevated, defined as hyperglycemia, the blood transforms. It becomes hyperosmolar and viscous. The excess glucose molecules, devoid of anywhere to go due to insulin resistance, begin to saturate the bloodstream. This isn't just sugar, it's a reactive chemical substrate that begins to bathe every cell membrane in a toxic, sticky fluid, fundamentally altering the hemodynamics of your circulation. Here, the chemistry turns destructive. Through a non-enzymatic process known as glycation, circulating glucose indiscriminately binds to proteins and lipids in the vessel wall. Imagine honey poured over a mechanical gear. The glucose forms covalent bonds with the amino groups of proteins. This structural modification fundamentally changes the shape and function of these proteins, rendering them stiff, malformed, and dysfunctional. These glycated proteins eventually degrade into advanced glycation end products, or AGEs. But AGEs are not inert debris. They actively bind to specific receptors on the endothelial surface known as RAGE, receptors for advanced glycation end products. This locking mechanism triggers a catastrophic intracellular signaling cascade, activating nuclear factor kappa B, a master switch for inflammation. The vessel wall is no longer just damaged, it is now actively signaling for its own inflammatory destruction. Simultaneously, the mitochondria within your endothelial cells are overwhelmed by the excess fuel. Trying to process this flood of glucose, the electron transport chain backs up, leaking superoxide radicals. This explosion of reactive oxygen species, or RS, creates massive oxidative stress. These free radicals attack DNA, lipids, and proteins within the cell, effectively rusting the vessel from the inside out and scavenging the body's supply of antioxidants. The most immediate functional loss is the quenching of nitric oxide. Normally, endothelial nitric oxide synthase, ENOS, produces the gas that keeps arteries relaxed. But under oxidative stress, this enzyme becomes uncoupled. Instead of producing protective nitric oxide, it starts producing peroxynitrite, a highly toxic radical that causes further cell death and constriction. The vessel clamps down, raising blood pressure and increasing the mechanical shear stress on the already weakened walls. In response to this injury, the endothelium expresses adhesion molecules like VCM1 and ICM1. These act like Velcro for circulating immune cells. Monocytes and T lymphocytes, which should flow past, are now snagged by the sticky vessel wall. They migrate into the subendothelial space, where they ingest oxidized cholesterol and transform into foam cells, the fatty, inflammatory core of what will become an atherosclerotic plaque. In tissues that don't require insulin for glucose uptake, like the nerves, kidneys, and retina, another trap awaits: the polyol pathway. Excess glucose is shunted into this alternate metabolic route, where the enzyme aldose reductase converts it into sorbitol. Sorbitol cannot cross cell membranes easily. It accumulates inside the cells, drawing in water through osmosis, causing the cells to swell, burst, and die. This osmotic stress is a primary driver of tissue damage in diabetes. Over months and years, the cumulative effect of cross-linked collagen and reduced elastin leads to arteriosclerosis, hardening of the arteries. The vessel wall loses its compliance. Instead of absorbing the pulse wave from the heart, The stiff arteries transmit this high-pressure shockwave deeper into the delicate microvasculature of the brain and kidneys, mechanically pulverizing the tiny capillaries that were never designed to withstand such pressure. Meanwhile, the fatty streaks mature into fibrous plaques. The core becomes necrotic, filled with dead immune cells and cholesterol debris. A fibrous cap forms over this toxic pool to contain it. But as inflammation continues, enzymes called metalloproteinases eat away at this cap, thinning it dangerously. We have now created a biological time bomb, a vulnerable plaque prone to rupture, which can trigger a sudden, catastrophic thrombotic event. Let us zoom into the microvasculature, starting with the retina. Here, the parasites, cells that wrap around and support the capillaries, are the first to die from osmotic stress. Without their support, the capillary walls weaken and balloon out, forming microaneurysms. These weak points rupture, leaking blood and fluid into the retina. The body attempts to grow new vessels to compensate, but these new vessels are fragile and disorganized, obscuring vision and leading to blindness. In the kidneys, the high pressure and high sugar attack the glomerulus, the central filtration unit. The basement membrane thickens in a desperate attempt to contain the pressure, but this only reduces filtration efficiency. Podocytes, specialized cells that prevent protein leakage, detach and die. Albumin begins to leak into the urine, a hallmark sign of kidney failure. Eventually, the glomeruli scar over completely, a process called glomerulosclerosis, necessitating dialysis or transplant. The nervous system relies on tiny dedicated blood vessels called the vasa nervorum. Hyperglycemia devastates these microvessels through the same mechanisms of glycation and ischemia. Starved of oxygen and nutrients, the nerve fibers, particularly the long ones extending to the feet, begin to degenerate. The protective myelin sheath strips away, causing short circuits in signal transmission. This manifests as the burning, tingling, and eventual total loss of sensation, known as peripheral neuropathy. In the lower extremities, macrovascular and microvascular damage converge. The large arteries feeding the legs narrow, while the capillaries feeding the skin die off. The skin becomes thin, shiny, and hairless. When a minor injury occurs, there is insufficient blood flow to deliver the immune cells and growth factors needed for repair. The wound stagnates, becomes infected, and due to the neuropathy, the patient may not even feel the spreading gangrene until amputation is the only option. The heart itself is not spared. Diabetic cardiomyopathy occurs independent of blockage, where the heart muscle itself becomes stiff and fibrotic from glycation. But the immediate threat remains the coronary arteries. When a plaque ruptures in these vessels, the coagulation cascade is triggered instantly. A thrombus forms, occluding the lumen. Heart muscle cells downstream begin to die within minutes, a myocardial infarction that permanently scars the pump of the circulatory system. In the brain, the damage is twofold. Large vessel disease increases the risk of ischemic stroke, while small vessel disease leads to a more insidious decline, vascular dementia. The microscopic vessels deep in the brain's white matter thicken and choke off, leading to silent strokes and cognitive decline. The metabolic chaos of hyperglycemia literally shrinks the brain over time, accelerating aging and disrupting neural connectivity. Yet, human biology is remarkably plastic. The concept of metabolic memory means past damage lingers, but immediate control can arrest the progression. When glucose levels are normalized, the production of ROS drops. The RAGE receptors are downregulated. The body's natural enzymatic cleaners, like glyoxylase 1, can begin to detoxify some of the AGE precursors. The endothelial cells can, to a degree, regenerate their glycocalyx and resume nitric oxide production. This is where lifestyle becomes medicine. Exercise does not just burn calories. Muscle contraction triggers the translocation of GLUT4 transporters to the cell surface independent of insulin, sucking glucose out of the bloodstream mechanically. It forces shear stress on the vessel walls, stimulating the eNOS enzyme to produce fresh nitric oxide. Dietary changes reduce the substrate for glycation, effectively starving the process that creates the sticky, damaging AGEs. We have traced the path from a single glucose spike to systemic vascular collapse. The science is clear. Hyperglycemia is a slow-acting poison that respects no anatomical boundary. But by understanding these precise mechanisms, the glycation, the oxidative stress, the pathway activation, you are armed with the knowledge to intervene. The vessel walls can heal, the inflammation can subside, and the silent damage can be stopped. The choice is biological, and it is yours to make.